Hello, this is John Perham here, that's me. In our first tutorial I did a couple of things off the record which I would like to repeat here and complete as well. The first was to recommend that you could enhance your understanding of three-dimensional surfaces by using the graphical capabilities of a computer algebra system such as Maple next time you're in the Maple lab. The second was to give a heuristic motivation for the formula for the normal vector to a generic surface given by an equation of this form involving a function of three variables. And I used that to derive the formula for the centripetal force acting on a particle moving on the surface of a sphere. So let's get going. So let's start with visualizing surfaces in 3D. And somebody asked me if I do question 1E, which is one of the difficult ones, and where we're asked to calculate the level curves, the YZ profile, and then plot the surface of the function Z of two variables, X and Y, which I can define as a Mathematica object, like that. And when I worked through this example, I mentioned how you might get insight into this kind of problem by investigating it in the Maple lab. I said that before. Anyway, I use Mathematica rather than Maple, but let us use the graphics capabilities of either to try to understand why the surface looks like it does, or even to find out what the surface looks like. So let's start with the level curves. So to find the level curves in the XY plane, we set this function equal to some constant c and solve for y as a function of x using this. And we can see that if c is positive, then this will only be real provided c is greater than the positive square root the positive square root of x, of c rather. If c is negative, of course, they're always real. So we'll start off with the level curve for c equals 0. In other words, in the plane z equals 0. That's what it looks like, and we can see these are straight lines, and let's see how they are related to the other curve. So we'll do the same graph, but now for c equals 1. And we'll plot that as a blue curve using this. And you can see it looks something like that. It looks like it might be a hyperbola or two sheets of a hyperbola. Well, let's do the same thing for c equals 2. And it looks something like that. That's the red curve. There we go. So that's what they look like for positive values of c. So let's now look at negative values of c. So we'll generate the same graph, but in green for c equals -1, like so. And this looks like a hyperbola, but now it's gone up the other way. And finally, we'll do it for c equals -2. Let's just fix that. And we can do that using that. And that looks like another hyperbola of the same type. So let's superimpose those 5 graphs, and we can do that using this. And you can see indeed that they appear to be hyperbolas, and for positive values of c, they're asymptotic to the lines in these parts here, and for negative values of c, they're up here. Well, that doesn't really tell us what the surface looks like. So to get a bit more information, what I'm going to do is to plot these curves at the appropriate heights, in other words, in 3 dimensions. So we can do that using this instruction. So we're using the 3-dimensional parametric plot function. So we have a function of x, and now we insert the value of y, and that's a function of x, and then we use the value of c. So it's a parametric curve, and we can visualize that all. And there, that's of course the the axes, and now we can do the curve for c equals 1 and for c equals 2. And just for fun, we've got c equals 2, we'll do c equals 3. And now we'll do the negative values using that for c equals -1 and for c equals -2. And then we can plot or superimpose all those three-dimensional curves using this. And that's what they look like. So for, oops, let's get that one back again. So for positive values of c, they look like they're some kind of hyperboloid up here, and for negative values of c, they're down here. Let's gives us some idea what they look like. So put a question mark in here. The next thing we're asked to compute or to plot is the YZ profile. So we set x equals 0 and plot z as a function of y. So that will look something like that, and it looks like that's a parabola. Well, just being curious, let's just plot the surface, because Mathematica and Maple have a facility for plotting functions of two variables, and we'll do that. And that's what it looks like. Do we believe that's consistent with what we've seen before? We can play around with this surface. So we can, and we, no, something went wrong there. So let's generate it again. So, let's, so it doesn't seem to want to do what we want it to do. Anyway, for negative values of z, we can see that that's down here, that we'll get hyperbolas pointing up that way. And let's rotate it some more. And we'll go all the way around now. So this is what the YZ profile should look like. So let's go around here and look again. And we can see for positive values of z, then there'll be a bit missing in the middle here, and so on. And for negative values of z, likewise here, there'll be bits missing in the middle, looking this way. So that's what it looks like, and I'll leave it up to you to decide whether that's useful. So anyway, I would urge you to, when you get hold of Maple, to have a look at this problem for yourself. So the other thing I tried to do last week was explain how the general formula for the normal to a surface comes about. So I'll repeat the reasoning here. So the left-hand side of the equation for a surface, or the generic equation, can be generated like that. So this is equal to 0. And in terms of the coordinates, which are x, y, and z, so we'll call those x, y, and z. Now, let's imagine a particle constrained to move on this surface. For example, if the surface is a sphere, then we'll have the motion of a pendulum. And such a motion can be described by a vector value function r of t, something like that, and we can establish that using this. So we'll call this r-fun, and it will be, the coordinates will be functions of time. Now, and if we insert these values into our original function g, then we will, presuming we know what they are, then we will get a function g of t. And we can do that by replacing the coordinates by the corresponding, or each coordinate by the corresponding component of the vector there. So let's do that. And so we can see, so this is some function of t. So we can differentiate it with respect to t using this. So this is the mathematical function which does symbolic differentiation. And this is what we get. So let's have a look what we get. We get z prime of t times this guy here, plus y prime t times this guy here, plus x prime t times this guy here. Well, these things here are the way that Mathematica represents partial derivatives. So in other words, G110 represents the partial derivative of G with respect to the first variable, and so on. So if we look at rewrite that, we can see that, whoops, this is not going too well, there we go, that this expression here is the scalar product of a vector containing the three partial derivatives of the function g with a vector containing the time derivatives of the coordinates. And of course, they're the velocities. So in other words, the scalar product of the vector of partial derivatives has to be perpendicular to the velocity. Well, if the particle is confined to the surface, it's not allowed to have any component of velocity normal to it because it would fly off. So we can thus conclude that the vector n, which is equal to the vector of partial derivatives, is the normal to the surface at that point. So let's press on. So let's do that for the case when we have an explicit representation of z as some function of x of y. So our g becomes x f of x and y minus z, and so the normal derivative is just the df dx, df dy, and minus 1, as is in the notes. So let's now look at this for the case of a sphere of radius L, so that our function g is just the Cartesian equation of a sphere, which is like so. And then if I differentiate that with respect to t, then what I'll get is that twice times a vector x, y, z, which is just the coordinates of the point, which for a sphere is also a vector in the direction of the normal, and the scalar product with the velocity equals 0. That tells us that the tangential component of the velocity is 0. So, but we can differentiate this equation once more again, or half this equation to get rid of the 2, and what we'll get is this. So we differentiate using the product rule, and the chain rule. So what we'll get is two terms. This guy here, which I've highlighted in red, which is just the square of the speed of the particle, and this term here, which is it's the normal component of the acceleration of the particle. So, and that's highlighted in blue. So what we have if we summarize or tidy that up, is we have that, we multiply it by the mass of the particle and divide by the radius of the sphere, then we'll have the mass times the normal component of the acceleration, which is the normal component of the force, is equal to minus the mv squared over L, so which is a well-known result in mechanics and elementary physics books. So I think we'll stop there.